Hello everyone, hope you guys enjoyed this week and ready for the final exams next week. Today I'm going to present a predictive model to calculate vehicular carbon dioxide emission. It's a very interesting topic because sustainability is a hot topic nowadays, considering the current climate, and we should all contribute and help in this matter. This is Ahmed Arida presenting, so let's get things started. So these are the main points that I'm going to cover today in my presentation. I will first start by the motivation and research questions and follow that by the data source and whether it's a reliable source or not. Then I will walk you through the data description and a brief description and definition of each feature in the data set. Then we will show you how I built my models and which model is the best for later use. And finally, I will conclude my presentation. First things first. Uh, the motivation and research questions is the first part on this list, so let's get into that. So why do we care about carbon dioxide? Carbon dioxide, or in short CO2, contributed and actually still contributing to what's called the greenhouse effect. And basically, what happens here is when a sunlight enters the atmosphere and it's reflected by the Earth's surface back to space, the atmosphere is full of CO2, which works as a mirror, and it reflects the carbon dioxide back to Earth. The main question here is what is contributing to the CO2 emission? As stated by the Environmental Protection Agency, EPA, transportation alone contributes by around 29% of the atmosphere CO2. So, because in the US, the main transportation mode that is being used widely here is personal cars. I'm analyzing a data set that has been gathered for personal cars mostly, and accordingly, my hypothetical questions are, the first one is, what is causing higher levels of CO2 emissions? I'm actually talking here about the micro scale of the vehicle. So I'm analyzing the characteristics of the vehicle and the corresponding CO2 emission from this vehicle. And the second question is, can we predict CO2 emission from other variables, from any other variables, and we can build, or in another way, can we build a good model from this data set? So let's get started by the data source and the data source description. The data source here is from, as I mentioned before, there is an agency that is responsible for vehicle fuel economy in the US. They test each model intensively each year and provide a summary of their findings to the public. This agency is Environment Protection Agency that I mentioned before. By the way, it's a division under the US Department of Energy. Accordingly, our dataset is reliable and we can rely on the results that we get out of this research. A good prediction model is an output of a good understanding of the dataset. So let's understand the structure of the dataset first and see how each variable is contributing to the output. So first, this dataset here is an open source dataset, which is provided on the Fuel Economy website. The fuel economy is actually the EPA website. The dataset has around 2,000 observations of different vehicle make and type with 18 feature, and the dataset is collected at the EPA lab and by the manufacturer engineers. So we can say actually it's very accurate. So we can depend and rely on the dataset. Here are the features that are included in the dataset. The name before the column is the name used in the dataset as an abbreviation for what's after the column. Uh, for instance, the word model is a short for the model name, and DSPL, the second word, the second feature, which is the decibel, it's a short for engine displacement in liters. Um, I will walk you through each one separately, but first, while we are here, I just want you to know that all features that are in blue coded are used as predictors, while the black bold one is our response. So the last one is the number 18, which is our response, and in any other feature is our predictor. I will be dropping 3 or 4 features from the predictors because they don't really contribute to our model later, like underhood ID. For instance, it's an ID each car has, so it doesn't really make any difference to the model. Also, the air pollution score is actually related to our response. So it doesn't make any sense that I predict a response that it's related to the predictors. And here, I mean, I'm actually conducting this research, or I'm building this model because I want to ease the process on EPA people in predicting the CO2 emission. So if I use the air pollution score, people there will still do some tests to get the air pollution score. So I'm trying to ease that. So I'm just skipping this feature here so we can ease the process on EPA people. Also, on the bottom part of this page, you will see a quick description of the data set. This is very useful to know or to have an idea how the data is distributed quickly. For instance, the displacement feature, the second column here, displacement feature may show a skew distribution because the mean, median, first quantile are very low compared to the maximum value. For instance, here for the displacement column, the minimum is 1.2, the first quantile is 2, the median is 3. However, the maximum value is 8, which means the data set is distributed. The distribution here is skewed to the right. Also, by looking at this table, we can confirm that we don't have any null values that we should worry about, since we don't have any word with NA with any count beside it. Here, I am giving you a glimpse of what each feature means in the data set. So it's easier for you to interpret later what the result or how the model is constructed and what feature is contributing more to the result. So for instance, in the first picture here, we have a conceptual presentation of an engine. So consider this an engine with 4 cylinders. So each volume here is a cylinder, and the engine usually has 4 of these, so we have here 4 cylinders. So like I said, each one of these is a cylinder, so we have 4 cylinders in here. And by the variable that has cylinder, that means the engine has a set of numbers of cylinders, and the displacement here, or the decibel, the engine displacement, is the sum of all volumes of these chambers or these cylinders. And by the way, it's important because the volume here is very important, or the engine displacement is very important, because this is the amount of fuel that the engine can burn in a one cycle. And then in the second picture here, we have the transmission type and the gear number. The transmission type, we have, if we recall the transmission type before that we had, which was called manual transmission. This is where you were supposed to change the gear manually yourself. However, we have different types now. We have the automatic, we have continuous gear change type. We have different types in here. Also, the gear numbers, which is represented by the gears NO, or numbers. On the third vector here, we have the drive. The drive is a short for the drive axial type. So some cars has 2WD, is a short for 2-wheel drive, and others have 4WD, which is a short for wheel drive. So basically what this means is, for two-wheel drive, the engine is only rotating only two wheels in a car. However, in 4WD, the engine is rotating 4 wheels in the car. For the fourth vector here, we have vehicle class. So the vehicle class is usually is the car a sedan, for instance, or a SUV? Is it a truck, or the type, or the class of the vehicle? The last one is the city MPG, which is mile per gallon, and I'm pretty sure that every one of you understand what MPG means. So we can go back here to this table down in this slide. So because we understood the features now, so we can read the description more better now. For instance, for the cycle, the cylinder, sorry, the minimum value here is 3. That means we have vehicles with three cylinders in their engines, and the median value is 6. That means that the average number of cylinders in the data set of each car is 6. However, the maximum is 16. So we have some cars that has 16. However, if you look here in the third quantile, you only see 6. That means there's quite a jump in here in the cylinder number of cylinders. Maybe this indicates we have an outlier or something. For the gear type, we have AMS, auto, and we have almost the same, the distribution here is very okay. That means most of them have the same the same number of frequency for each gear type, except for the auto manual type. And here it has a very low number of vehicles. For the gear numbers, the minimum is 0, and the 0 here means there's this type of gear that is continuous. This one, it's CVT. It's a continuous variable transmission or something. I forgot the exact abbreviation of it. But this gear type, it's very continuous and it's very smooth. So the gear, it's really hard to know the exact gear numbers in the gear type because it's very smooth. It's like a Tesla or something. So it's very smooth and it has dozens of gears inside it. And the drive here, we only have 2 WD and 4 WD, and both are almost equally distributed. And for the fuel, we have a very large number of vehicles with gasoline fuel, and very few with diesel, ethanol, and gasoline, electricity and gasoline together. And actually, for the certified region, this is one of the variables that I discarded because it doesn't contribute or do anything to the model. So we will just discard this variable later. And for the vehicle class here, you see they are equally distributed. And for the air pollution, I canceled this feature like I said before. And for the city MBG, mile per gallon, we have the minimum is equal to 8 and the maximum is 100. So we have a big range in here for the city mile per gallon. And I'm not sure if you see the last variable, which is the CO2. So it has a very similar distribution, or it's almost a normal distribution in here. So what we have here is the pairs plots. So I'm just reminding you in the in the far left side of it, we have the displacement and the cylinder numbers. And as you can see, I'm just reminding you from this plot, if you can remember that we have the cylinder numbers is the number of chambers or these bars in the engine. And by increasing it, that means we are also increasing the volume of the displacement. So yeah, that means that there is a relationship between both of these in here. Also, at the same time, if you look on the right side, where we have the blue rectangle here. So if you're trying to see the city MBG and the highway MBG, of course they are not the same, but they are following the same trend. That means we have a strong linear relationship between both of these. And for the combined MBG, actually the combined MBG is calculated from the highway MBG and the city MBG. It's the average between both of them. And of course, that means the relationship there is a strong relationship between both. That means we have multi-collinearity in the data between those variables. So also for the com.co2, this is our response. So it's very clear that we have a second degree relationship between the CO2 and either the city MBG or even highway MBG. But there's a little bit of deviation. It's not just a smooth line. So what I will be doing in our model, that I will try to fit as much as I can by other variables, not just the city MBG. So as I said before, definitely in this data set we have outliers. So to investigate this more, so I plotted the vehicle classes and the gear types versus the CO2 emission. And to see better, I used something called violin plots. And in violin plot, here, for instance, for the vehicle classes, on the x-axis I have every vehicle class with the corresponding CO2 emission. And if this, for instance, for a small car, if this white area is very wide, that means the distribution at this part is very large. I mean, the frequency at this part is very high. However, if we have very narrow line like this, that means the distribution is very flattened at this part. So if I'm trying to draw a distribution for instance, for a small car, it will be like that. And it's very flat at the end of it. So that means this part is an outlier. So, and also I did the same for the gear type, and I found both we have a very obvious outliers in both different visualizations, and both pointed out that we have 3 different makes that are doing this kind of distribution. So it's these 3 kinds are Bentley, Bugatti, and Lamborghini. And for the gear type, it's AMS. I think it's the automatic manual transmission type. Now let's jump to building our models. So first thing, I divided my data set into 2, the training set and testing set, and I said For the training set, I will just dedicate 70% of the data set for it. And for the testing set, I set the remaining of the 70%, which is the 30% of the data set. And by the way, they are randomly divided, so I didn't bake it up. I just randomly selected the data set of the training and testing set. So the first model that I built had the formula that is equal to the response, which is the CO2 emission is equal to almost all the variables in the data set that I can predict on. And the result is the R square, which is equal to 0.9657, which is 96.5%. And here the F statistics is 1054, and the p-value is very, very small. That means our model is worth it. And then I did the VIF analysis, and I set the threshold to be 5. And then I found there's no value that is exceeding 5. That means I don't have any linear relationship between any variable in the model. So this model is good. So I said, why not we increase our predictability? So I said the significance of the make variable was very, very low. So I said, why not we get rid of this and try again? So by the way, before that, here is my error analysis from this model. As you can see, the error is almost normally distributed except at the tail here and at the other tail. And as you can see, there is kind of a trend in the data set this model didn't capture. Maybe this is a trend. Maybe this is a trend as well. So maybe the model didn't capture second degree of the variables, or it's 1 degree here as a linear relationship. So for the second model, I removed the make variable and I did the same analysis, and in this time the R square was 0.953, which is a little bit lower as expected. However, the F statistic is 2500 this time, and the p-value is very low. And as you can see here, this is the error analysis. Again, you can see the same trend in the dataset and the same trend, in the error analysis. And the error is almost normally distributed, but for the tails, they are a little bit off. So I said, let's just try the stepwise regression if there was interaction. By the way, I kept all the outliers in these models, and then I will run the same models without the outliers, and then at the end we decide which model is better based on the output and error analysis. So in this case, we had the stepwise regression with interaction, and the R square here it's almost 0.99. And the F statistics is 1216, and the p-value is very, very small. However, in here, if I run the VIF, as you can see here, since I have the threshold is equal to 5, so any value that is beyond or more than 5, that means there is a linear relationship between or there's a relationship between between this value and other values. For instance, for the displacement variable, the VIF value is equal to 65, which is larger than 5. That means there is a multicollinearity in these variables, so I should remove the displacement first and then rerun the model again and see if there's any value on the VIF greater than 5. I should rerun the model again until I get all the values lower than 5. So I removed all the variables or all the interactions that are their VIF values greater than 5, and then this is the output or the resultant model. So as you can see here, the R square is a little bit dropped to 0.97 with the F statistic of 1624, and still the p-value is very, very small. And here you can see here the trend is a little bit deviated or removed, but you can see there is a little bit of a trend again, but it's not as strong as it was before. So I said, because we're trying to, in the field, we don't have time to calculate all this long equation. So in the last model, so I said we need to simplify the model as much as we can. So I said I will just include the most significant variable in the dataset, which is the log city.mbg. And then as expected, the R square is reduced to 0.92%, 92%, and the F statistic is very, very slow as well. However, the trend is seen here. That means and this actually indicates that there is a trend in the data set. Maybe it's a second degree, as it's obvious, very obvious in this error analysis here. So I said maybe we should include another variable that is square of the logcity.mbg. So this is what I did here. So I included both. So it's the logcity.mbg plus logcity.mbg square, and the output is much promising. It's 96.5% with the p-value very, very low. However, the F statistic is much, much higher this time. And here you can see the error doesn't seem to be having any kind of relationship or trend, and the distribution of the error is better, and it's normally distributed now, and you can see it's much more better even in the normal QQ plot. And then I decided that we should remove the outliers and try again for the best models. Remember, our best two models now is the LRR and LR simplified, where we only use the log MBG and log MBG square. So I removed the outliers and I run the model for the LRR, and this is the result here. It's almost normal this time, but it's deviated at the tail of the normal distribution. So I said maybe we are if we try the other model and we can see and we compare between both. Remember, this time we have the R square is equal to 0.97. So the other model here, I just kept both the log city and log city square, and as you can see here, it's much better actually compared to the last model. However, these three values or couple values up there that deviated the normal distribution of the error. So I said it's time to compare between all these models together and see which model is the best to use later and provide for the EPA people to use later. So what I did here is because I divided the dataset into two, the test and the training sets. So I used for the first part, which is the BIC and EBIC. I used the BIC for comparing the resulting model on the training sets. So the first part is I'm using the training set to compare. So for the BIC, you can see the lowest value is LRR model, which is the longest model. And the probabilities here is this is the best model here because this value is 1 and all other models is 0. However, when I was trying to run this model and validate it on the test data set, I found that LR simplified 2 is much better in predicting the data set that the model wasn't trained on. So I said LR simplified 2 is the best model to use later. So to conclude here, I'm just comparing between the best two models here. So it's actually the simplified model that I'm recommending people to use, which is the CO2 emission is equal to the log city MBG plus log city MBG square, which gave me the R square is equal to 96.5%. However, if you need much better model in accuracy, it will be this very long model. It will give you 97.7%. However, this model is over-predict in the data set. So that means if we're trying to generalize this data set, this model, and use it for other data set that this model wasn't trained on, it won't be as accurate as this. So we can just discard this model completely and rely and use only this model, which is the simplified model 2. So at the end, I just need you to. So these are my references that I used in this research. Thank you very much for your listening, and have a good day.